Hey everybody, we're going to talk about how we select different antimicrobial procedures and the different factors that influence that choice. So there are four major factors that we're going to look at. The type of microbe that we're going to try and get rid of, the environmental conditions that we are dealing with, the risk of infection to others, and the composition of the item that we're trying to get free of microbes. All right, there we go. So there are a lot of types of microbes, and some of those microbes are very resistant to antimicrobials. So we have our basic vegetative cells like E. coli that we might be able to get rid of relatively easily. But then there are some cells that produce endospores. Endospores are very resistant. It takes a lot of heat or chemical treatment to destroy them. Protozoan cysts and oocysts. These are also resistant. So these are things that we would find in fecal matter, and we can't, it's hard to destroy them. So not as hard as bacterial endospores, but still hard to destroy. Just a basic chemical disinfectant isn't going to do the job. So you would have to use a stronger method like boiling. Mycobacterium species have mycolic acid in their cell walls, which makes them very resistant to chemical treatments. But autoclaving is a mechanism we can use to kill them. Pseudomonas species is super resistant to disinfectants. In fact, it grows in disinfectants a lot of times, and this is one of the reasons why Pseudomonas species can be or can cause so many hospital-associated infections, because you have Pseudomonas growing in some of these disinfectants that we're using. And then I talked about enveloped viruses and how we can inactivate them by washing. There are also viruses called non-enveloped viruses. So they don't have that lipid envelope, and because of that, they're harder to inactivate. So when we're looking at the types of microbes, we also have to look at how many microbes are in the environment. So anytime you're using an antimicrobial procedure, you're only going to kill a certain number of microbes per period of time. And so when microbes die, they die kind of the same way they grow. So they grow exponentially. They die exponentially, but they die at a slower rate exponentially than they grow. And so their reduction time, decimal reduction time, or the D value, is the time required to kill 90% of a population under specific conditions. So the conditions would be, what's the temperature? Is there oxygen available? Is there no oxygen available? So those are the types of conditions we're looking at. So to reduce a population of 1 million bacterial cells using a D time of 5 minutes. So that means that every 5 minutes, we're reducing the population by 90%. And the goal is to get less than 1 cell remaining. It would take 7 D times. So there are 2 mechanisms for doing this. I'm showing you one mechanism, my preferred mechanism. You can take 1 million and multiply that by 0.1, which is going to give you the same, or by 10%, either way, 0.1 or 10%. It's going to give you the same number as this. So if you multiply 1 million by 0.1 or 10%, you're still going to get 100,000. Another way to do that, it's known as decimal reduction time. So you reduce the decimal, you move the decimal over 1 place to the left, and you go from 1 million to 100,000. After 2 times, you move it over 2, you get 10,000, then 1,000, 100, 10, 1, and less than 1, that means there's no cells remaining. So it takes 7 D times, and since the D time is 5 minutes, we take 7 times 5, and we get that 35-minute time limit. So I have a couple questions that I came up with that I think will help you. So I'm going to show you the answer, but I want you to try to figure this out on your own first. So before you go on, pause the video and try and see if you can figure this out. Okay, so before we do anything else, before I give you the answer, I want to remind you that we're killing off microbes at 90% of the microbes are killed with each D time. And in this case, the D time is 15 minutes. So every 15 minutes, we're killing off 90% of the population. Population started at 42 million, okay? So what does that mean to us? I already mentioned this before. You can do it 2 ways. Multiply the total number by 10% or 0.1 to get the new total for each 15-minute period, or reduce the decimal by 1 for each 15-minute period. And the answer, for those of you who did the work, hopefully you got 8 D times at 25 degrees Celsius. And you can figure that out by going 1, 2, 3, 4, 5, 6, 7, 8. If I asked you how long this would be, say I said, how long does, oh, I did ask you how long it will be, sorry. So it will take you 2 hours. So 8 times 15 is 120, or 2 hours. Here's another question that I can give you. Population of microbes is killed off in 12 minutes. So we know chemical X kills all the microbes in a population in 12 minutes at 21 degrees Celsius. We also know that there were 1,345 microbes in the initial population. So how long is the D time? So now I'm asking you to tell me the D time. So again, pause this and try and do the problem. All right, so now let's look at the actual answer. We know that there are 4 D times because there are 4 digits here in the number. So that means 1 D time, 2 D time, 3 D time, 4 D time, right? To get that decimal over beyond the 1. So if we divide the 4 D times into the 12-minute period, we get a total of 3 minutes for each D time at 21 degrees Celsius. It's kind of fun. Other conditions that we're going to look at is environmental conditions, so type of microbe, environmental conditions. We're going to treat the microbes differently if the environment is very dirty. If we have dirt or blood in the environment, we're going to have to do different things. You can't just put Neosporin on here and expect that it's going to take care of the disorder or the scraped knee. This one's very clean, so of course you can just put the Neosporin on and cover it up with a Band-Aid. So first you're going to have to wash this, and then you'll have to put the Neosporin and the Band-Aid on. The risk of infection. So there are different risks for infection. I'm going to go from the bottom. So non-critical items such as stethoscopes or blood pressure cuffs, we're not going to worry about as much because they aren't as risky. They're not as likely to transmit a disease. But anything that is entering our mouth or any body part, we're going to be more likely to treat differently so that we don't transmit disease. We're going to use different chemicals, different sterilization methods. Critical items have to be sterile when you use them, and you would not utilize something, a critical item in general, between patients. So you're not going to use needles or scalpels between patients. You may use the same scalpel after it has been sterilized again. Needles we never use between patients. And then the composition of the item. So what is it made of? I put these because obviously, you're not going to treat this um, microbial infection the same as you would treat cleaning a toilet bowl to get rid of the microbes. So you're going to definitely use some type of cleanser on the wound, and then you're going to use, so you're going to use an antiseptic on this after you've cleaned the wound. Over here, you're going to use some disinfectant to keep the microbes away. I'm going to stop here. It's been 10 minutes, so that's a long video, and we'll get into heat methods for destroying microbes in the next video.